My dear students of CE806, Structural Analysis and Design of Concrete Structures to Sessional, Breeze Part, lesson number 9. In this lesson, we will be discussing about the articulation point. Articulation is called articulation. Standard name is articulation. It is jointing two parts of the simply supported span of middle span will be jointing with the cantilever part of the main breeze part, and this is also known as hubbing joint, hubbing point, because we will make the simply supported span end portion of half depth and the cantilever part last portion as half depth to match with the normal breeze depth and to show nice thing in the elevation. In this point from the simply supported span, we have a shear value of shear force value of 222 kip from 64 simply supported span, and as I have said, to keep the depth of the girder same as the simply supported girder, it will be required to widen the section for taking care of shear force at the section. So for this widened section, an increase of 2% of extra load is added with the main shear force value. So VA is equal to 1.04 into V0, and our simply supported span in the main bridge design, we have seen that this V2, that means at this point shear force was 222 kip. That's why by increasing it, we will be doing this BA as you will note where is BA will be acting in the next page. This is 226.5. The FA shear friction, from here we have to go ahead with this. When this breeze will at temperature at difference of temperature, increase of temperature and decrease of temperature, this breeze will move, and surface to surface shear will be there, surface to surface friction will be there, and that shear value will be 0.05 of VA, and this 0.05 of VA gives us 11.5 kip. For this, we have to put some extra steel in the horizontal position of this joint. Next page. Here is the whole picture of this joint. At the top figure, we have shown the elevation of this joint. As you see from left, this 54 inch is the main girder depth, and the 82 inch is the girder depth at the interior support at the end of cantilever, and the right hand simply supported span beam depth is 54. You can see all these figures, 54, 82 and 54. These are the basic figures, and we will make it hub as the joint. We will be keeping this bottom line in match with the original breeze, original section. That's why we will keep it as 54 inch, and 27 will be at the top, and the 27 inch will be at the bottom, and in between there will be a bearing plate. There will be a bearing plate. Above the bearing plate, the portion is known as depth. This term is depth, and the depth of this depth is 27 inch, and the bottom portion is named as ledge. It is 27 inch at the face, and for the normal beam slope of the anchored span, main span, the bottom portion will be sloped. Bottom portion will be sloped towards the support of interior support, and this is the situation, and this is the section, and the black portion is the bearing pad. The black rectangular portion is small, black rectangular portion is the bearing pad. These bearing pads are neoprene pad. These are still embedded in these pads, are still sheets are embedded in a special type of rubber, and the these are found in different sizes and the different sizes, and there will be these will bear the load through this pad. The load from the top portion, that is depth, will transfer to ledge portion, that is ledge portion. And we have to first of all find out the size of this pad, bearing pad, size of this bearing pad. The bearing pad is made sufficiently strong. It will not squeeze. If there is any little deformation, that will not affect the whole design of the bridge. And the size of this pad, bearing pad, neoprene bearing pad, depends on the concrete strength, and that bearing criteria, from bearing criteria we have found out the dimension of this bearing pad, and we will be showing we will go through those lines by those description line by line. First of all, we must describe some other part. There must be the pad will be the center position of this ledge and depth. Ledge and depth part. The plate will be at the center, and from the face of the center there must be at least 7-inch clearance from the outside of this structure from all direction. The 7 inch is minimum. If we want to, if the section is more, then we can keep it a little more, 8 or 9 inch also, but minimum you have to, all through of this pad, this black pad. The plan is shown in the bottom figure with a line diagram, and this PPP are shown from side, and the BB is the width of the, BB is denoted as, the width of the pad is denoted as BB, and the length of the bearing pad will be decided. First of all, we have to find out the, choose about the width of the pad, and one is to be kept fixed, otherwise we cannot find out two with single two dimension in single equation. That's why normally will be the width of this BB or width of this pad will be about 8 inch, 10 inch and 12 inch. If whatever is available in the market, we must know about those available size, and from that available size we have to find out the length. This can be cut and used in this position. The calculation here will be bearing criteria calculation will be the bearing stress on the bearing area shall not exceed the concrete bearing strength FB. Therefore, FB minus BA is equal to BB is equal to or more than BA. BA is the force calculated on the top line of this right hand side of this portion, and BB is the width of the bearing pad, and FB is the bearing stress. FB is the bearing stress, and 2P is the 2P are the side clearances. BA is equal to and here bearing strength FB is bearing strength FB is 0.85 phi F prime C. FB is 0.85 phi F prime C. Phi is for bearing strength phi value. 0.85 is a factor for this equation, and phi is the bearing stress reduction factor, and that is 0.65. In shear we use this factor as 7.5, and for moment we use this factor as 0.9, but in bearing we have to use this factor as 0.65, and F prime is our original concrete strength chosen, and we have designed the whole structure with 4 KSI concrete strength, and FB is the 0.45 0.85 is the equation form factor, 65 is the pi factor, and A prime is the concrete distance, and that gives us a value of 2.21 KSI. The pad area will be 226.5 is the load here, and this 226 divided by 2.22 will give us a value of 102.5 inches square. Taking B as 8, as I have said, in the market there are several sizes, 8, 10 or 12. If we choose the B as 8 inch, the length will be coming as 12.81 inch in calculation, and in practical we will be using as 14 inch. And in this phase, these are the factors. Here in this phase, another point is there. We have calculated a value, FA value, shear friction value. FA value is given as 5% of B2 and is equal to or more than 0.2 of more than VA. And we have to calculate 0.2 VA or 0.5 B2, and from this, whichever is bigger, we have to use that one. And in this case, we have to find out, we have to see one thing, the effective depth of the ledge. Effective depth of the ledge we have to calculate. In the ledge portion, the bottom portion is a slanting, a sloping line. We will approximately take this sloping line and take at the end of this cantilever part, we will increase this 27 inch. 27 is the half of the 54 inch simply supported girder depth, and 27 is from there, and we will as the interior support is 82 inch, and we have to meet these two 82 and 54 in a sloping line, and that sloping line is shown here. That's why for this ledge, the depth near the cantilever, at the end of this cantilever, there will be something more than this 27 inch, and we have to increase this by 2-3 inches. And these are the points in this. These are the points in the space. We will go to the next page. Here calculation will still for moment. The moment AB is equal to the distance. In the previous page, we have shown at the top of that page what is AB. AB is the center. AB is the distance from the center of the bearing pad to the face of the joint. And there 7 inch is the 7 inch is the clearance. 7 inch is the 4 inch is the half of pad, and 7 is the edge clearance 7 inches, and there will be this the AB distance is 4 is half of 8 inches. 7 is the P value, and 3 is the gap required for expansion. 3 is the gap required for expansion. That we have to keep a gap for expansion, and that's why this 3 is there. 3 is the expansion gap, 7 is the bearing pad edge value, and 4 is the half of the bearing pad dimension, and this gives us 14 inch. And the moment MA, the center of the load is at the center of the bearing pad, and this AB is equal to 14 inch. That's why moment will be AB into 14 inch. We have, and the force was 222 kip, as we have earlier calculated. as earlier we calculated 222, keep. And this moment term is 14, this is the moment, and next one is the another part is 43.5 into 25. 43.5 is the FA value, 43.5 is the FA value. This 25 is to be in this equation, MA equation, this 25 is to be explained. This 25 is to be explained. The FA into FA is BA is equal to BA is 222, keep, and AB is equal to 14, and this 43.5 is FA, and the depth of this, the moment arm is 25 by, because our the ledge depth we have taken as 25 inch, and at the center will be the moment, and that is this to be divided by 25 by 2, and these two figures gives us a value of 3646 inch. Here FA is 222, we have shown it earlier, and B for AB is equal to 14, we have shown in the calculation above, and 44.5 is the FA value, and 25 inch is the depth of the ledge, and the center, the moment will be coming up as the center will be 25 by 2, and the arithmetic calculation gives us a value of 3646. Ink calculation of D, it is taken as 27. I have shown that the 27 is the end of this ledge. 2 to 3 inches for 2 inches for slope. This is increased by 2 inch for the slope, and is deducted 3 inch for effective depth by 3 inch, and then effective depth here is 26 inch. These 2, 3 and 2, these are explained in this written form. Therefore, we have to find out AS for M is equal to 3646. Normal style we can find out this steel area and the number of bars. I believe there is no necessity of explaining this portion, because the moment is 3646, and the steel yield distance is 60, and depth is 26 minus A is taken 3, and that's why A by 2 is 1.5, and this gives us a 2.76. It's simple calculation, and by checking it we get a value of 3 inch, and no matter check the area is used 1 inch dia bar for 4 numbers, 1 inch dia bar 4 numbers.
For piston.
In this equation is a little bit clumsy and a little big equation, but we have to solve it, and we have to know this is a very exactly a new equation, and the equation is written like this, and shear friction criteria, to fulfill this shear friction criteria, we have to just use this given formula, and we have to note this value, which one is what. Then phi is normal shear, for shear phi is 0.75 here. C is a cohesion factor, it's a given factor, it's a known factor. In this stage this 145 cannot be explained, but it should be taken as cohesion factor as 145 psi, 145 psi. ACV and mu and ABF, etc. These are the values we have to put here. Mu is given, area of is 24 by 28, and this mu value is in this equation, shear friction equation, mu value is 1.4, it's a given, and ABT and 60,000 is the FY. ABT is 84,000 into ABT, and with this arithmetic equation, solving this, the ABT is to be found out, and all these are numerical values, and with calculation of these numerical values we can find out ABT, and the ABT is 2.43 inches square. For this one, for the shear friction criteria, you have to use 2 number of 10 bars. Area will be coming as 2.54. We have we require 2.43 inches square. Steel area for FA. We have calculated FA value in the previous page, and here also we are showing that FA is equal to 220 into 0.05. 222 is the force, and the reaction force or bearing reaction force, and 0.05 is the factor, and this is 11.1 kip. For this 11.1 kip shear friction factor, we have to give 11.5 divided by this. As this is skipped, we have to directly divide it by the allowable stress, and there the phi factor will be there, and the phi factor is used here is 0.9, and the value is 0.2 inches square. Use half inch dia 1 number for this force. Steel area for VA. Our VA is 226.5, and AS is equal to VA. Directly we have to calculate this steel area by dividing allowable stress. Allowable stress is 60, and phi factor is 0.9, and that gives us a value of 4.19 inches square. Use 1/3 inch dia bar 3 numbers, and also we have to find out the stirrups for these two sections, because this section is half section, and shear force is the total shear force, and both this total shear force will be acting at the top portion and also at the bottom portion of the segment, and here the DA will be have the normal beam depth. In the simply supported beam depth, whatever it is 50, 60, 54 inch or whatever it may be. The here we have got is 27 inch, and from this 27 inch we have to find out the effective depth, and then we have to calculate the spacing of the stirrup for normal shear and normal shear. And this much for this lesson. Thank you.